Hey, the Pythagorean Theorem is probably a topic you find hard to avoid rushing into the algorithm. It's often taught, probably the most, as this kind of plug and play formula. It's like, here's the formula, let's plug in the numbers from the diagram, and let's go. So in this video, we're going to shake things up. We want to bring about the Pythagorean Theorem. What activities, what lessons do that the best? We've got one here for you. Let's go. Hey there, Math Moment Makers. John here from Make Math Moments. If you have not yet subscribed to us here on YouTube, make sure you do that. Hit that bell, hit that subscribe button so that you can get the videos coming to you when we release them. And we're releasing one every single week here on YouTube. So in this video, we talk about this new lesson that we've been building. It's actually a 4-day unit on the Pythagorean Theorem where we start with unpacking and using our students' prior knowledge of area of composite figures and how we can use that to actually bump into the proof or a proof of the Pythagorean Theorem. And students actually will see this relationship between congruent triangles and congruent squares and make this connection between the areas of the squares off the side lengths of a triangle. So that would be like the day one task. And in this video, we're going to show you a sneak peek, a classroom sneak peek of me doing this lesson with my class remotely online. So stick with us. Also stick with us after the video. I'm going to show you the task that I used and how you can use that task in your class, and also all 4 days of that task. It stretches over 4 days, going from introduction into the Pythagorean Theorem to actually solving problems, complex problems with the Pythagorean Theorem of all types. So stick around after the video for that. And you're going to get your typing fingers ready, and you're going to write down things you notice and things you wonder. Remember last time we did this, we did it on the Desmos activity. And you typed it in, and somebody were like, "I don't know what to notice. Like, I'm so confused." Now that we've gone through that, that's normal to be like, what is going on here? Now you know that, hey, it's okay to write anything you like here about anything you notice and anything you wonder. Now, what we're going to do is I want you to get in the chat. We're going to do a chat explosion here, where you're going to write down things you notice and things you wonder in the chat box, and put a comma between them instead of hitting enter. If you hit enter, it'll probably send it to the screen. Okay, hit a comma after you wrote something you notice, and then write something you wonder or something you notice. Give me a couple notices and a couple wonders, 2 of each to start. Okay, 2 of each. It's a very, very short clip. I'm going to play it a couple times because it's so short. I'm going to kind of go back and forth a little bit. So get your typing fingers ready. All you got to do, don't hit enter. We'll hit enter all at the same time. Let me bring it up. What do you notice and what do you wonder? That's it. That's it. What do you notice? What do you wonder? I'm going to just do that animation one more time, folks. Here it comes. What do you notice? What do you wonder? One more time for you. Here we go. What do you notice? What do you wonder? I'm going to leave that up on the screen for a moment. We're going to hit enter all at the same time. Just put commas again after. I'm going to give you 1 minute more think time. Okay, 1 minute more think time. So quiet like think time. Here we go. 1 minute. All right, here we go. I'm gonna kick us off the main screen right here. Are we ready? Here we go. On the count of 3, I'm seeing in the chat explosion. Here we go. 1, 2, 3. Give it to us. Look at them fly in. Look at them fly in. Okay, let me. Yeah. Anything you notice? Anything you wonder? Let me go through a couple of these. I'm just gonna read them out loud here. Okay. Let me bring this picture back up on the main screen though, so that we can notice and wonder these things together. Okay, 1 square. Okay, pretty typical. We got a big square here, and this person's saying 1 square, 4 triangles. I wonder what it's for. I wonder what it is. Yeah, I wonder what it is. Very common. It's like, what's going on, right? We've got why, just why, Mr. Orr. when is there a box in a box? Why did you show us this? I love that, right? We love that question to come up. We're going to answer that for sure coming a little later. Jeremiah says, the square became a diamond and then the same size or the diamond might be slightly smaller. So I think this student's wondering, are they the same size or is the diamond slightly smaller? Another student says here, I noticed they changed a square to a diamond shape. I noticed there's 4 points. I wonder why they did that. Why did we do this? I wonder what's the point of this. Very good. Very, very common question. We want to know what the point is of this. We will definitely answer that today. This student says made a shape and they all went the same way. Yeah. I noticed a diamond in a square. We got the diamond in the square for sure. I noticed the square is a diamond. Very, very common things. Awesome. Thank you for noticing those things. I also noticed those same things. I also wondered one extra thing, and actually a student in a previous class wondered this one thing that I thought was worth exploring, and I want to explore here with you, is if we think about this diamond that's inside this square, and I guess one wonders, is this actually a square, right? So are they a square? Like what we talked about that yesterday. What makes squares? But I'm wondering this. I'm just gonna have you visually do help us answer this question right here. Common question here is this one right here. Like how many of these little things, like these little squares? I'm gonna tell you that they're squares. Okay, so how many of these little squares right here, that little one that you see right there, how many of those little ones are going to fit in that middle square? And I'm actually going to tell you that that is a square in the middle. I know some of you are saying diamonds, but I guess if you take a diamond and you tilt it, you've got, or so you take a square and you tilt it, you got a diamond. So I've got this little square here, and I've got this big square here. I'm asking you, how many of these little squares would fit in this big square? Okay, so I'm going to do an estimate here. Now, I'm going to ask you to do another chat explosion, but I want to do 3 chat explosions on this. Okay, we did this. Let's do it this way. I want you to give me some wrong answers. Okay, wrong answers only. Wrong answers only. But I'm going to be specific about the types of wrong answers here. I want you to tell me, but don't hit enter. You type it in, get it ready. I want you to tell me a wrong answer of how many of those, right? The question is, how many of those little squares fit in the middle square? This, let me see, that middle square, not the big square, the middle square. How many of those fit in there? Wrong answers only, but I want the wrong answers to be like, it's too small, right? There's got to be more than blank little squares. Okay, type it in and we'll hit enter at the same time. Type it in, we'll hit enter at the same time. We'll do the chat explosion. Wrong answers only. It's too small. Like the number you're going to tell us is lower than what the actual answer should be. Okay, here we go. Give me a too small, and don't tell me a range. Tell me an exact number, like you just picked. I know this is too small. Okay, here we go. 1, 2, 3, go. They're still coming in. They're still coming in. I like it. They're still coming in. We got a lot of too smalls, and these are clearly too smalls. Like we've got Jaden who's saying, yeah, for sure, 3 is not right. And I agree with you. You've hit the nail on the head there. 3 is not right. 3 of those, if I stack those inside here, 1, 2, 3, that's only going to take up like this little tiny portion in this corner. 3. All right. 3 is wrong, right? For sure, it's too small. I'm wondering if anyone is riskier than 3, though. Like, I wonder how risky we can get with how many are in there. Like, I wonder. Any riskier people than 3? We see a 4. Dylan said 4. That's a little riskier than 3, but not much. Give me another one, folks. Throw in the chat. What would be another risky number that's wrong for these little squares to fill this middle square? Like, it's got to be like Julianne's saying like 25, 10. Like I think I could fit 25, maybe even across here, right? Dylan, we've got 50 now. We're getting riskier. We're bringing that risky factor up. And so I wonder now, give me another, like here, yeah, 78. I think 78 is still wrong. Like I think, and it's still too low. So good stuff. Let's give another wrong answer here. Come down from the top. Give me a really large number that's too big, right? It's like there's no way this many of those little squares fit in the middle square right there. Give me a huge number that you think is wrong, but also, yeah, 1,000,000 wrong for sure. You're like, there's no way 1,000,000 fit in there. Like 2,000, like, yeah, be risky with like your number here, like 10 million billions. I see like a huge number, like 876,000. These are huge numbers coming in. I agree with you. These are all, I gotta be wrong. Like Caden's just filled the screen up with numbers. That's probably, yeah, it's probably wrong. You got it. It's too big. We want to think, how risky can you be? So some risky ones I think are like 1,000, 2,000. We got 160, 110. It's tough to gauge, right? Okay. So if it's tough to gauge, this is what we did the other day when we were looking at R2D2 in the post-it notes, is if it's tough to gauge, what I want you to think, and get your typing fingers ready. What extra information could I tell you to help you narrow down this, right? Remember, mathematics, anybody can guess, but with more information and strategies, we can narrow down to having a very precise answer. So what about this diagram would you like to know more about so that you could narrow your prediction? I want you to think about that for a moment. Okay, I'm going to give you 1 minute think time. You can type it in the chat and get it ready so that when we hit enter, we can look at those chat explosions. Okay, so think carefully. What information would you like to see in this diagram? And we're going to talk about strategies, because that starts to, when you start to think about what information you want, you're going to start by nature just thinking about a strategy you can take to try to figure out how many of those little ones fit in there. Okay, think of those. I'm going to give you 1 minute think time and type time. Go ahead. All right, here we go. On the count of 3, I'm going to look for some info coming in from you guys. What do you want to know? 1, 2, 3. Hit enter. Here we go. Any other info? Hit enter. I've got a couple coming in. I'm going to read them out loud. Here we go. Here we go. I'm going to read them out loud. We've got interesting surface. This student wants to know the surface area of the inside square and the tiny square. Okay, so this is, I think, in relation to the R2D2 problem we did yesterday, that if you knew the area here of the inside square and the area here of the little square, you could figure this out. Okay, so we could figure this out. Another student says, how big is the small square and how big is the tiny square? We're trying to fit in. So similar questions. Like if I told you a size dimension of this square and the size dimension of this square, we should be able to figure this out. I like it. I like it. Now, does anybody want to be brave with, like, if I told you that information, how would you figure that out? I'm going to give you some of this information. So here's where you come in. This is going to be your part now. I'm going to give you some information, kind of like we did before, yesterday, or actually day 1. And I would like you to draw me your solution. So you're on paper, pencil, pen, ready to go. You want to do this on a device and type, like, you know, maybe you're working better by using your, say, tablet or maybe paper. Whatever is the best method for you to show your thinking. I want you to do that. And I want you to show me how you get, like, how many of those little ones fit in that one, okay, in the middle square right there. But I'm only going to show you this. I'm actually not going to give you as easy of a situation as we did the other day with the R2D2 post-it notes. It's a little bit sneakier. I'm being a little bit sneakier. So we want to see how clever your strategy can be here. So have a look, okay? I'm going to show you this instead. I'm not going to show you exactly the size of the middle square. I'm going to show you the bigger square. So I'm going to show you that 12 of those little squares, the little squares, they fit across that portion of the large square. Okay, so up to that dot. And I'm going to also reveal a little bit more. I'm going to reveal the rest of that length at the top. Okay, so check this out. The rest of that length is 16. So I'm showing you how many squares, 12 on that one side of that dot and 16 on the other side of that dot, are across the dimensions of this big square. Okay, the big square is 12 here and 16 here. Those little squares are the same little squares as that one right there. Now, I did say it's a square, so if we look down the side, that's 16, and that's 12. All right, I'm going to leave that there. This is the information I'm going to give you. So with that information and your knowledge about area or wherever strategies you want to take here, I still want to know how many of those little squares fit in the middle square. Okay, that's the main goal here. So I'm going to give you a good chunk of think time here. I'm going to give you 10 minutes think time for sure. Okay, so I'm going to turn off my camera. You're going to work on a piece of paper. You're going to show some strategy. You're going to show some calculations or whatever strategy you're taking. And then you're going to send that picture to me. I'm going to put that link back up. This is the same link we've always used for sharing our work to each other. Okay, so it's coming back up here. It's the joinkh.com. We log in with our Google account here. I'm going to put that in the middle of the square just so you can see it clearly. You're going to want to draw this diagram here on your page to show you what's going on here, and then show me your work to figure out how many of those little guys fit in this one. I'm showing you some dimensions across here, okay? So I'm turning my camera off. Is there any questions before you get started on showing some thinking? In about 10 minutes, I'm going to come back and see where we are. Some of you guys asked for the sizes of the two squares. Like they wanted the size of the little one, like on our R2D2, we wanted the size of the Post-it note. That's similar. Like, what is the size of that? I didn't give you the size of that. I showed you, hey, there's this many goes across the top of this square, and then there's this many on the width of this square, and then from that we were going to solve a problem. So here's where we are. I'm going to show you some solutions that got started and some solutions that were end. Remember that the solutions I show here are anonymous, as well as they're not all the solutions. I can segment off just to show a couple. Okay, so I've got just a couple to show, and then we're going to walk through a visual representation of this in a moment. So right here, if I bring this solution across, notice this one right here. This one is super common. I'm gonna outline it here to showcase that this is definitely a great start to this problem. Okay, so notice all we really know are the dimensions of the big square. So this student says, look, all I know, Mr. Orr, are the dimensions of the big square. So why don't I figure out the area? This is what I'm seeing from this solution, right? The area, by outlining it the way they have found the area of the big square in terms of how many of those little squares. So for example, if 12 plus 16 fit across the top, that's 28 little squares across the top. That's 28 little squares down. That means length times width, since it's a square, or 28 squared, 28 times 28 is 784. They said, I think, they didn't say anything here, but what that means is there's 784 little squares that fit in the big square. Okay, so that's the whole square. There's 784 squares fit all the way across, all the way down, filling the diamond, filling everything. Okay, so that's too many. That's too many. But it's a great start. I think we need to start there for sure. So bravo to that student who submitted that starting thinking. So super important. Excuse me. All right. While I think that same, here we go. I think that same strategy's now been updated. Actually, why don't we peek at that same one? I've got a new picture. It looks like it's the same person, because it's the same picture, but now we've updated it. Okay. Ooh, I like this, because while I was talking, this one just came in. So check this out. We've got an updated version on this picture, which I think looks pretty good here. Does anybody want to speak? Can be brave here and speak to the strategy after the one I just outlined how many squares fit in the whole thing. But does anybody want to talk about what's going on here? Can you help me out?
What they did was they found the area inside the big square, And
Yeah,
then,
yeah, that was this up here.
yeah, found the area of all the squares surrounding the little square. And then minus that from the big, like, overall, and got the area of the small square.
Okay, let me repeat what you just said, just to make sure. You said the area of the big square Madison had calculated, which we talked about, which is 784 little squares fit in the big square. And then you said something that was interesting, that caught my ear. You said then she found the area of the smaller squares. Is that what you meant to say?
I meant to say that the, like, both in the corners.
The triangles in the corners. Got you. Okay, so I can see that here. There's the triangle, area triangle formula, which was base times height divided by 2, is 12 times 16. Now, if we come back here and look at the diagram, this triangle here, if we are assuming this is a right triangle, which we got to if this is a square, right? Then this is a right angle here. Then this is the base. If this could be the base of the triangle, 12, this is the height of the triangle at 16. And we did 12. Let me bring this back. 12 times 16 divided by 2 gives us 96, I believe. 96. And then, Jaden, do you want to say why this was multiplied by 4 then?
Because there's 4.
There's 4 of them. Let me just double check that they're all the same triangle here. This one has 12 and 16. If I look at this bottom corner triangle, this is also 12 and this is also 16. So I guess, like, this is height is 12 and this base is 16. I guess you're still multiplying 12 and 16 together. So, and dividing that by 2, you should get the same answer. There are 4 congruent triangles here. Congruent meaning the same, right? Identical triangles here. There are 4 of them here. So in this Madison solution, she multiplied that area by 4 and said, hey, there's 384 squares in the triangles. And then what happened here again?
She minus the she big square minus corners.
Big square. We took the big squares, and we took out all the little squares that would fit in the corners of the triangles, and we're left with 400 squares. Put your hand, do a hand raise if you also got 400 squares. Couple. Nice. Okay, let me look at another solution, right? We're going to look at a couple solutions. I think that was very clear as well. The solution is very nicely detailed and outlined. Let me bring up another picture that also has 400 squares here, folks. Look at this one. This one's got a visual. We've got the big square here. I like how they used U for units. Very nicely done. They look at this detail. I really like how this triangle is clear over here, that they've brought out the triangle and said, look at, we're going to look at that one triangle. It's 12 times 16 divided by 2. We get 96 units. There are 4 of them. That's 384 units, square units. And then they did that same subtraction to say, hey, it's the big squares units, take away the corner units of 384. They got 484 square units there. Nice work there on that solution. I really like the visual nature of that one as well to go with the calculations. I'm going to bring up another one that is the exact same strategy. This one is the 28. There's that same 28 by 28, so 28 squared. And then there's the triangle base times height divided by 2. We get 96. There's 4 of them. We get 384. And then we subtracted them to get the 400 small cubes. Nice work there. Let me show you another strategy. Pardon?
That was me.
That was you. Feel proud of that one for sure. Hey, look at this. We've got another one here. Same strategy and same answer. Okay, I'm gonna actually give you one more extension problem on this. I'm gonna actually leave this this one up since it was the last one I showed here. I'll just show you that there's 400 small squares in there. There's 400, so it means like that area of the little the diamond, the square in the middle, has 400 square units. It's 400 square units big. That's the area of that square. I'm gonna challenge you right now in the chat to find the dimensions of that square. What would be the length and the width of the little, like the diamond square, the square in the middle? What would be, if there's 400 square units inside that square, what would be the dimensions of that square?
20.
Wait, where's this 20 coming from?
You do 400 and then you do square root and it gives you 20.
Thank you. We just said it was 400 units, and we were working on that the other day, that we were going to square root to find its dimensions, and we get 20. Nice. So which means that there would be 20 squares that go across this diagonal right here, right? So that would be 20 by 20. Hey, 20 times 20 is 400. Nice work being an area of a square. So congratulate yourselves, folks, on figuring out the area of the middle square, or the number of little ones that fit in there. And you've done it in a nice strategy with finding the areas of the big square and the areas of the triangles on the edges. All right, good stuff. Now I'm going to show you, I want to show you this other technique. There's another strategy here I want to show you on the main screen. So make sure you've pinned me. I want to show you that another student did this differently, and they visualized this in a very, very unique way. Okay, so I'm going to show you that right here. So all you got to do is watch this. I'm going to walk you through it. This student said, you know what? Hey, there's those triangles that you guys noticed. What I'm going to do is I'm going to rearrange those triangles. Look, if I put that triangle there and I put that triangle there, then I could, that's the same thing, right? And so the empty space in the middle, the big square, is the same as the empty space in these two new squares that we've created. And look, I'm going to fill up this square here because I know its dimensions. I know that that top bigger medium square is 16 as width. And look, it's the same as that other one, so it's 16 by 16. And so that would be 16 by 16. That's 256 little squares so far that fill up the empty space. Hey, look at the dimensions of this little other medium square down here. It's 12. It's 12. Oh, let's fill that up. Okay, so we're going to go 12 times 12. What's that going to be? How many is going to fit in that square there? Let's fill those up. And notice this, what's happening here is the same empty space in both pictures, is that you've got these two smaller squares that end up being the same area as the big square. And if you look really carefully, then those smaller squares are attached, if you can see it, attached to the right triangle, right? It's the same right triangle that's in all four right triangles. If you look, that the height of that triangle was 16 and the base of that triangle was 12. And if you draw the squares, or look at those squares off that triangle, so let me show you a little bit more clearly here. So notice that areas are the same. If I add those two squares up, I get the 400, just like you guys did. So they did this a little differently. But look, this triangle, I have the height of that triangle, it's 16, and we created a square by rearranging those triangles, and it was 16 by 16 is 256. And this, this base was 12, and 12 times 12 is 144. And if I add those two things together, I get 400, which happens to be the area of that inner square, which is also the square off the diagonal, which we call the hypotenuse of that triangle. That worked in this situation, right? Like it worked by rearranging the squares, and we get this scenario here, which is a fancy relationship here. Does anybody know the relationship between these three squares? What this is called? It's got a fancy name. If you don't, that's okay. We're going to talk about it. But in general, watch this other animation right here. If I have any square, like you have shown in your picture, and I create these same congruent triangles off the sides, just like your diagram, but I don't know the lengths, and we rearrange those triangles again, we can create an expression to help calculate the area of the middle square. So if I say, hey, look, that diagonal is c times c squared. You guys did that when you did this problem. And if I rearrange those, though, look, the c squared is the same empty space as those two squares that are defined by the side lengths of the triangle. So we get this thing called a squared plus b squared is c squared. Does anybody know what that is? I'm going to play this one more time. That this big empty space is that length times that length, so c squared, which is that empty space. And hey, if I just rearrange these, that square plus that square is equal to that square. But that square is the b squared, and that square is the a squared. And so those two areas added together give us that area. And but those two areas, let me hang on here. Let me just adjust my movie here. So notice if in right here, these two squares right here are built, like the height of that triangle was b, and that's b squared. The square kind of built off that triangle. And the base of this triangle was a, and there's a square based off a. Those two areas add to that area. And that area, look, in the same diagram, whoops, in the same diagram, that square is the square off the diagonal, off the hypotenuse. That's the fancy name for that square right there. That's called the Pythagorean Theorem. The Pythagorean Theorem relates the three squares together by saying, hey, if I got a right triangle like this one here, this right triangle in here, and if I have this length and this length, then I can find this diagonal length off that triangle by squaring the small lengths and adding them together. Give me a hand raise if you've heard of the Pythagorean Theorem. Yeah, we've heard of it, but maybe not visualized it in this way. So here's what we're going to do. We're going to take a short break here because we've gone over time a little bit. We were going to break at 9:30, but we're now going to break. All right, we are back after that classroom sneak peek. And again, if you have not yet subscribed to us here on YouTube, make sure you hit that button to subscribe and get notified when we have our next video go live or get released. All right, so as promised in the intro, I talked about a task that I use with my students called squares to triangles. And what I want to do is show you where you can get that task and how you can actually access all four days of that task. So if you head on over to makemathmoments.com/tasks, you will see our tasks there, and you can find the squares to triangles task. And here's what the day one task looks like. So this is the task that I used in that classroom sneak peek. Just day one you saw. There's the video for the what do you notice, what do you wonder? There's an image. Here was the estimation prompt. You can play these right from in your classroom, or if you're teaching remotely, you can show these right on your screen right here. We've built them so that we've stripped all the teacher moves away from some of the videos here in these tabs. But if you're looking for those teacher guides, we do have the guide here for the teacher for you. So so in this task, we talk about what the big ideas are. But if you scroll down, you can get all of the instructions and also the recap videos of like the sense making of showing this proof of the Pythagorean theorem. So that's what's in the teacher guide. All Make Math Moments Academy members have access to all days of all the teacher guides. And so you can get that there. There's again, I had some follow-up questions after my lesson. I didn't show that in the classroom sneak peek, but they are here on the website. Some consolidation prompts and a student handout here. If I go right to the top and head to the reflect area, you can see that you can get some prompts there for your students to use as well. Now, if I jump over to day two, let me give you a sneak peek at what day two looks like, because in day one, we kind of bump into the Pythagorean theorem of talking about the areas of the squares. But in day two, we do an investigation of looking at the areas of squares off any sort of triangle. So if you look at the side lengths of any triangle, build squares off the side lengths, much like the proof of the Pythagorean theorem, not just right triangles. What do we see? What do we notice about seeing some of the areas combined when we have acute triangles or obtuse triangles? Trying to, we actually kind of bump into the triangle inequality there as well. And in this purposeful practice, there is some practice there to do after the students do a full investigation. On day three of this task, we start with a math talk by asking students to fill in some areas, and you can use this right off the website to kind of show the pictures and ask them to write down areas, write down values. They're meant to be quicker calculations, but bring out the idea that, hey, what happens when we do not know one of the side lengths of the shorter legs? And so that's that version of the Pythagorean theorem, and bringing out the visual. And we have some purposeful practice in terms of appointment clock structures and some fun activities there. And then we end on day 4 with applications of the Pythagorean theorem. We have another problem-based tasks called corner to corner, where you see me string a string from one corner of the room to the other, and you have this 3-dimensional version of the Pythagorean theorem that kids will have to solve in that day 4 task. So that's 4 days task. You can get that by heading on over to makemathmoments.com/tasks. And all Academy members actually have access to all the teacher guides of every single day, with all the student handouts and the slides that we all the animations and the slides built right into the slide deck. So you can download those as Academy members, and you can join the Academy free for 30 days on heading on over to makemathmoments.com/academy. So love to see you over there and join the 1,000 members we got in there, who are sharing ideas, helping each other use the tasks, and also our professional development courses are all in there too as well. So awesome. How have you been teaching the Pythagorean theorem? I know it's a hot topic. It's also really a favorite, of people to teach that topic. But I'm wondering what you're doing. Let me know in the comments.